Welcome to E21. So today's lecture will be the 23rd. And a few announcements, inshallah, homework is posted and inshallah do Wednesday, 11:59. Quiz for inshallah on Wednesday. The material is 7.1 to 7.6. Let me just go over what we did so far in chapter 8. If you recall, in chapter 7 we had a situation where we have either a resistor and an inductor or resistor and capacitor. But starting from chapter 8, we studied the case where we have a resistor, capacitor, and inductor in a same circuit. So there are two possible configurations. There is one, there is a parallel configuration, means that the resistor, the capacitor, and the inductor are in parallel. And there is another configuration, which is the series configuration, where the resistor, capacitor, and inductor are connected in series. So we started with the parallel combination, and we're going to spend so much time on it compared to the series combination, because once we master the parallel combination, the series combination is it's almost the same. The only difference here is the number of frequencies. That's the only thing that's going to differ. So when we derive the natural response, we were interested in the voltage across the parallel combination. So we derived this differential equation, and we showed that the solution is of the following form, where S1 and S2 are called the characteristic roots, because those are the roots of the characteristic polynomial. And A1 and A2 are constants that depend on the initial conditions. Okay. So this is the characteristic polynomial. This is the polynomial that has S1 and S2 as its roots. Notice here, S1 and S2 could be complex, and this is the situation where we have underdamped response. Alpha is less than omega naught, and it could be real, and of course it has to be negative, otherwise the system will not be physical. And this is the case where we have overdamped response. And the last possible scenario is when you have one root with multiplicity of 2, means that S1 equal to S2, and this is called the critically damped response. So we see that if we have an overdamped response, we have this form of the solution. If we have an underdamped response, we have this form of the solution. And clearly here, in this form, there's some sort of oscillation. But this oscillation is bounded, and it's going to be eventually zero as t approaches infinity. And the last response is the critically damped response. Forget about this one. So in the previous lecture, we solved exercises on after introducing every type of response, every type of responses, we solved one exercise. In this lecture, what we're going to do is we're going to start with one exercise, but we don't know what type of response we have. This is usually the case. So, in all problems, it's less likely that you will be told this is an overdamped, or this is a critically damped, or this is an underdamped. But you will be given a circuit with certain parameters, and from that you can deduce what type of response you have. So let's see what we have in here. In this circuit, we have two switches, this switch and the other one. And these two switches operate synchronously, meaning that when switch 1 is at position A, switch 2 is at position B. Then when switch 1 moves to position A, switch 2, when switch 1 moves to position B, switch 2 moves to position D. Moves to position C. Okay, let's see what happens. what we want to do, we want to find the voltage across the resistor here for t greater than 0. Okay, in this circuit, always the very first thing I encourage you all to do is what? Hadi?
Draw the circuit.
Yes, exactly. We need to draw the circuit. So let's draw the circuit for t less than 0. For t less than 0, we have a 5 ampere source in parallel with 250 and 160 millihenry. So we have basically we have two circuits, two separate circuits. And we have 25 microfarad in series with 75 ohm and in series with a voltage source. So from these two circuits, what can we deduce? Yes, sir.
We can deduce the initial current and initial voltage for both the inductor and the capacitor.
Yes.
It will be 5 ampere and 100 volts.
Exactly. So the initial current in the inductor can be found from this circuit, which is going to be 5 ampere, and this is going to be I naught. The initial voltage across the capacitor is going to be 100 volts, and this is equal to V. Okay, now we found the initial values. Now let's consider what happens when the switch 1 moves to position B and switch 2 moves to position C. Okay, this is what happens for t when t greater than 0. So now we have 160 millihenry inductor with initial current, and we have 25 microfarad capacitor with initial voltage. So now we have a parallel RLC circuit. We know that the solution could take one of the 3 possible solutions. So what should we do now? Mohanna?
We start by finding alpha and omega to determine the type of circuit.
Okay.
Is it underdamped, overdamped, or critically damped?
Okay, so let's start with omega naught. Omega naught is 1 over square root of LC. And if we do that, we'll get 160 milli 25 micro, and this is going to give me 500 radians per second. Okay, what else? Ibrahim?
We should find alpha, which is 1 over 2RC.
Yes. And if we do that, we will get 1 over 2, R is 50, C is 25. And in this case, you'll have 400 radians per second. Okay, now I found alpha and find omega naught. So clearly here, alpha is less than omega naught. So this response is under damped. So if we know the under damped, we know that the response is under damped. We know the standard way of solving this problem. The solution should have the following form. Okay, so what's missing here? We are missing B1, B2, and omega D. طيب, Ziad, what is omega D?
The square root for alpha square minus omega naught square.
Omega naught square. It's going to remember here because we already assumed that this is complex, so we already took this into consideration. So it's going to be and this one is actually clearly it's going to be 300. Think about it this way: if you have a triangle with 1, 3, and 4, then by Pythagorean theorem, this one should be 5. And this is exactly it. طيب, what else, Abdulkarim?
I need B1, which is the initial voltage.
So how to find
How to find P1 minus alpha P1 plus WG P1 equal IC initial over C.
or could be something like this. If you substitute 0, you'll get P1. So what's the initial voltage? Is going to be the initial voltage across the capacitor, right? Because this one is in parallel with the capacitor. So B1 is 100 volts. Okay. Mohammed, question? Okay. So now what is B2? So if you have, here's the thing, Shabab. If you want to find the coefficients for an initial value problem, is you need to create some sort of like independent solutions. So in general, in differential equation, if you want to find the coefficients of initial value problems, then you need to find the you need to solve the derivative. You need to solve the function itself and its derivative. So the function here is Vt. We solve we substitute into this function using the initial value here. Now we need to use its derivative and substitute using the initial value. Right. Okay, so then in this case we need to take dv by dt. Remember, this is related to the current passing for the capacitor, and this must be equal to. Oh, let's first find the current passing for the capacitor. So what's the current for the capacitor? Yes, sir.
Maybe because we know the voltage, we can calculate the current in the resistor and then use KCL.
Yes. So it's going to be V0 divided by R. minus the initial current in the inductor, and this is going to give me -2, -5, -7 inductor. Now I know the value of the capacitance, so I can easily substitute. So IC divided by C equals to -7, 25, which is microfarad, equals to, this one is -280 volts per second. And if I substitute if I differentiate this equation and evaluate it at 0, I will get minus alpha B1 plus omega D B2 equals to, remember this term is equal to IC divided by C, which is we found it to be 280,000, negative 280,000. So B2 now is minus 800 volts. Okay, now I found B1, B2, I found alpha, I found omega D, so now I can easily write down the solution. Alpha in this case was 400 T, cosine 500 T, I'm sorry, 300 T. Minus 800 the unit is volt, and this is 240 kilocalorie. Okay. So now, what did we do with chapter 7? So we started with something called the natural response, which is the response when you're trying to discharge your circuit or discharge the capacitor and the inductor. Then move to step response, where you have capacitor and inductor, then you start charging them, you connect the source to them. And this is exactly what we're going to do here. So we're going to move to the step response of the parallel RLC circuit. Okay, in this case, again, we need to derive, or we need to come up with a differential equation that governs this system. So we have a current source, and this current source is in parallel with resistor, capacitor, and inductor, and also in parallel with a switch. So when the switch is closed, all the current will flow in this branch, and nothing will flow here. Then when the switch is open, current will start flowing in these three branches. So by KCL, considering the case when the switch is greater than 0, when the time is greater than 0, when the switch is open, you will have the current, applying KCL, you will get this formula. So if you substitute IL plus, what is I here? V divided by R. What is I of the capacitor? dV by dt equals to I. Now, if you recall what we did when we derived the natural response, we differentiate both sides, so we end up with an equation in terms of V. But here, think about it this way: if you do that, it will not reveal, it will not lead you, or it will not lead you to the final current in the circuit. And this need to be, in this case, we need to actually solve, or we need to present the differential equation in terms of the current. So let us so the voltage of the inductor or the voltage is related to the current. So this is the voltage across the inductor, which is exactly the same as the voltage across the capacitor, which is exactly the same as the voltage across the resistor. Now, if I differentiate it with respect to time, I will end up with L di L dt squared. So now let me go back and substitute. So you have IL, V, which is L di by dt. So L divided by R, dIL by dt. Now I have dV by dt, which is L di squared by dt squared. So in this case, I will have LC dIL by dt equals to I. So if I put it in the standard form, I will end up with the following equation. And if you see this differential equation, it's exactly the same as the previous one. The only difference here is that we're solving for the current instead of the voltage, and we have an initial, or we have a non-zero. We have non-homogeneous differential equation. We have a forcing factor that comes from the fact that you have source. So you would expect the solution to be something similar, somehow similar, and this is exactly this is exactly the form of the solution. So it turns out that if you have this differential equation and you want to solve it, then the solution will be, it's going to be exactly the same as the case of the natural response. There's only one additional term here, which accounts for the final value of the voltage, for the current, and the final value of the voltage. Therefore, if you have a, say, like an overdamped response, what will be the solution of, what will be the natural response solution? It will be A1 multiplied by e to the power s1t plus A2 multiplied by e to the power s2t. So the only thing that you need to add is the final value. Something like this. Similarly, if you have an underdamped response, also if you have an overdamped, if you have critically damped response. So you see exactly the same form of the solution. The only thing here, the only thing that you need to add is actually final value. So you can think about this problem as the general form, and the natural response is a special case. Why? Because in the natural response, the final value is what? What's the final value of the natural response? How shall I? Muhammad?
0?
Yes. So the natural response is a special case where IF is equal to 0. So this is the general form of the solution. The natural response there is a special case when IF is equal to 0. So if you are to solve this problem, if you are to solve a problem that involves a parallel RC circuit, then you can easily assume that it's a step response. If it happens that IF is 0, then it's actually a natural response circuit. Then it's actually it's a circuit that we are interested in the natural response. Ahmed?
يعني دكتور القوانين هذه تعتبر نفس القوانين السابقة؟
Yes, exactly. Exactly the same. So if you remember, this is what happened if we have an overdamped response, صح?
صحيح.
If the only thing that we did
ضفنا عليها
is
زيرو
IF.
اللي هي زيرو.
If we're talking about the natural response, yes. But if we're talking about step response, then it's non-zero. So you can assume that it's non-zero, and you can assume that this is the standard form of the solution. And if you end up with IF equals to 0, then it's a natural response. واضحة؟
ايه نعم يعطيك العافية.
Let's just try to solve this problem. Talal, question? Talal, you're muted. Talal, ما أسمعك. طيب طلال. طيب let's see. We have the following circuit. It's a parallel RLC circuit. The initial energy stored in the circuit is 0. لا طلال ما أسمعك هنا. The initial. So you can ask your question. Please type it very quick. This is just an exception. Okay, in this circuit we have an initial energy. We are told that the initial energy stored in the inductor is 0. Or then the circuit is 0, which means that the initial voltage and the initial current in the capacitor and inductor, the initial current in the inductor is 0, the initial current in the capacitor is 0. Then at t equals to 0, a DC current source is applied to the circuit itself. Okay. So what we are asked here is we are asked to find the initial value of the current across the capacitor. Talal, yes, that's exactly what we do. Okay, so let's see what we have. So we have a circuit, and we are told that the initial value or the initial energy stored in the circuit is 0, which means that the initial voltage across the capacitor and the initial current passing for the inductor are both 0. Then at t equals to 0, a 24 milliampere source is applied to the circuit. The resistor is 400 ohm. So what we are asked to do is we are asked to find the initial value of the current. So what's the initial value of the current? Abdullah?
I think it's 0 since there is no energy stored.
Exactly. So the initial value of the current is 0. Okay, what about the initial value of the derivative of the current? So what is the derivative of this current? Walid?
It's also 0.
It's also 0 because, let me just write it down. Note that V equals to L dIL by dt. And we know that the voltage is exactly the same as the voltage across the capacitor. And we're told that there is no initial energy stored in the circuit, so the initial value of the voltage across the capacitor is 0, which means that the initial value of the voltage across the inductor is 0, which means the initial value of the derivative is also 0. Okay. So we solve the first two parts. Then we're asked what about the roots of the characteristic equation? What are the roots, S1 and S2, of the characteristic equation, Ali?
We find first alpha square and omega naught square.
Exactly. Let's find alpha first, then we take the square of it. Alpha 1 over 2 R, we are given the result is 400. This one is 25 nano. And this is going to give me 5 times 10 to the power 4 radians per second. So alpha squared is going to be 25 times 10 to the power 8 radians squared per second squared. Omega naught is 1 over square root of LC, or let's say omega squared is 1 over LC, and this is going to give me 16 times 10 to the power 8 radians squared per second. So what type of response we have? I need new names. What type of response we have? Ahmed, Nafi? Ahmed.
The omega naught is greater than the alpha.
No, alpha is greater than omega naught. So we have an overdamped response. So if we have an overdamped response, what kind of roots we have? If we have an overdamped response, what kind of roots we have? طيب Ibrahim?
Real roots.
Yes, exactly. So S1 will be minus alpha plus alpha squared minus omega naught squared, which is going to be minus 20,000 radians per second. S2 is going to be minus alpha squared omega naught, which is minus 80,000 radians per second. So now we found the roots of the characteristic equation. Now the last thing is we are asked to find the numerical expression for I L of t when t should be greater than 0. Greater than or equals to 0. Okay. So let's write it in the standard. Let's write the standard form of the solution. So we have I final plus A prime S1t plus A2 prime S2t. So what is the final value? Let's start with the final value. So what is the final value in this case? What's the final value here? Ziad?
Minus the current source.
Not really, it's the current source. It's not the minus the current source. I final is 24 million bare. So now we need to find A1 prime, A2 prime. So the first thing is we need to substitute the initial value. So IF plus, if you substitute 0, you'll get A1, A2. And this is going to be, remember the initial value is 0. So this is going to give you 0. The second thing is you need to take the derivative and you find the initial value of that. And if you differentiate, you will get, and evaluate it at 0, you'll get S1 A1 prime plus S2 A2 prime, and again, this one is equal to 0. So you have two equations, two unknown. At this stage, you know how to solve it using your calculator. So you see that A1 prime is minus 32 milliampere. A2 prime is minus or 8 milliampere. So the solution is going to be minus or so 24 minus 32 e to the power minus 20 thousand t plus 8 e to the power negative. The unit is milliampere, and this one is true for t greater than or equal to 0. Any questions about? Like, if you take this problem and you just adjust the value of the resistor there. So if you choose 500, then you will end up with critically damped response. If you choose for example 600, 625, you will get with the underdamped response. So if you plot the current versus time, remember that in all of these cases, because it's exactly the same circuit, the only difference here is actually the resistor, the value of the resistor, and that value of the resistor does not change the final value of the current. Remember, because at the end of the day, you will have an inductor that behaves like a short circuit, and the value, anything in parallel with short circuit is 0. So the final value will be the same as the value of the voltage of the current source, and in all of the three possible cases, you will have the same current source. So eventually, you will end up with 24 milliampere. So if you have an underdamped response, you will see that, or let's start with an overdamped response. You will see that it will take a while to get to the final value. It will not reach it very quickly. The one that's going to reach it very quickly is actually the critically damped. The problem with, and also like the underdamped, but the problem with the underdamped, there's like an overshoot voltage. There's kind of like voltage that goes beyond or above the final value, and this could cause trouble in some circuits. So you see that you are shooting actually for critically damped, but the issue with the critically damped, it's a very single point here, meaning that you have to choose R to be exactly 500. However, if you take any physical resistor, you will see that it comes with tolerance. For example, if you have 500, if you have 500 resistor, sometimes it comes, sometimes it has 5% tolerance, which means that, or 10% tolerance, which means that it could be anything from 450 to 550. Even though this is when they tell you the resistor, they tell you that this is 500. We're saying that's 500. We are guaranteed that this is 500 resistance with, say, like 10% tolerance. So it's going to take any value from 450 to 550. If you design your circuit or your system based on a symbol or a single value or a single resistance, then for any slight change, any non-ideality in your circuit elements, your system will, for example, move to a critically or like an underdamped response, which is something you don't want. Therefore, to be in the safe side, you kind of like, well, the optimal solution is critically damped, but the suboptimal one is overdamped. So yes, I'm okay with the delay. I know that I'm not going to reach the final value very quickly, but I'm sure here that I'm not going to fry some other hardware because I have an excess current here. You see what I'm saying, Shabab? Is it clear? Karim?
Doctor, can I compare the the over voltage that I get with the underdamped? Like, can I use like I get too much? I get an excess amount of voltage. Can I just like put a really huge amount of capacitors and call it a day? Is that a thing? Like, is that possible? A huge amount of resistors, I mean.
No, the thing is like this also could affect, because if you add a resistor, in this case, you can affect the overall resistance, because remember, in this case, we are talking about the Thevenin resistance.
Okay, thank you.
Okay. So let's solve this exercise. I think this one is, we have two more exercises on this topic. Then we'll move to the series RLC circuit. Okay, in this circuit, this is somehow similar to the circuit before, and actually this is the underdamped, and this is the critically damped circuit. So in this case, we are told that the initial current is for the inductor is 29 milliampere, and the initial voltage across the capacitor is 50 volts. The source here is exactly the same as the previous one, and we are asked to find the current passing through the capacitor for t greater than 0 and the voltage across the capacitor, or the current passing through the inductor for t greater than 0 and the voltage across the inductor or the capacitor for t greater than 0. Okay, so in this case, let's start with the standard way of solving such a problem. First of all, you need to what? So I'm asking you to find the current passing through the inductor. What should you do? First of all, it's a parallel RLC circuit. صح?
صح, yes.
So what should you do? Karim.
I know that like I should draw it at the first moment. Then I know the current. I know the equation of the current that will go.
Okay. Why do you need to draw it?
Because because there's a switch and it's gonna be if I close the switch, all the current will go through it, and if it's open, all the current will be divided.
So what's the piece of information that you're going to get from drawing the circuit? The initial values, صح?
Yes, I get the initial current and the initial voltage.
You are given the initial values, so you don't need to draw it.
Yes, okay.
Yasser?
Yes, Doctor. So can you tell me what is the question again? What is required?
So
IL.
we're asked to find IL, the current passing through the inductor. So what should we do? What's the first step?
Okay, the current passing through the inductor. First, we know that the voltage across the capacitor is 50, so we can calculate IR. Oh no, hold on. We are given IL. Yes, we're given IL.
Yes.
Okay, so we should find I final, and it will be 24 milliampere. If I'm not wrong.
Okay, right, sure. Who else can jump in and participate? Ibrahim?
Maybe we should first apply KCL.
Not really, Ziad.
Verify what type is it?
Provide what?
Verify if it's overdamped, underdamped.
Yes. That's a fair question. Because with chapter 8, with the parallel RC circuit, we have 3 options. So we're not going to invent anything new. We have 3 options. Either we have an overdamped or critically damped or underdamped response. So we need first to know which response we have. If we know which response we have, we know the form of the solution. Okay? From the form of the solution, we can go and look for the missing information. واضح يا شباب؟
Yes.
Okay, very good. So we need to verify. So by finding alpha is 1 over 2 RC. 1 over 2 RC is R is 500, C is 25 nano. In this case, it's going to be 1 over 2. Omega naught, if you solve for it, you'll get so you notice here alpha is equal to omega naught. So in this case, we have we have a critically damped response. So if we have a critically damped response, then we know that the solution is something like this. I final plus d1 prime t Okay, so now let's look into this form of the solution and see what's missing. So we know alpha, we've calculated alpha. So we're missing I final and d1 prime and d2 prime. So let's start with I final. So what is I final in this circuit? I final is what? Ibrahim?
It is 24 milliampere.
Exactly, 24 milliampere. Okay. Now, in order to find D1 and D2, D1 prime and D2 prime, you need to actually know the initial value. So the initial value of the current, we are given that the initial value of the current across the inductor is 29 milliampere. The initial value of the voltage across the capacitor, which is exactly the same as the voltage across the inductor, is going to be, or it was 50 volts, and this equal to L because remember the voltage across the capacitor is the voltage across the inductor is L di by dt. So therefore, di by dt evaluated at t equals to 0 plus, it's going to be 50 divided by L, which is 2000 amperes per second. So now I can go ahead and substitute. So IL prime so we can clearly see that D2 prime is 5 milliampere. طيب. Okay, now we found D1 prime, D2 prime. We found the final value, so everything we need now is available. So we need actually to substitute. And this is simply the current passing through the inductor. Remember, the very first step is actually to know what type of response you have. And from that, you can see what values are missing and what values are needed and what values are there, and start finding the missing values. Now we found I of t. Can we find V of t, the voltage across the inductor? Ahmedani?
Dr. Why did we say that I final is 24?
Because what happens in this circuit, the switch is open for a long time. Just look into the circuit. What happens when the switch has been open for a long time? The capacitor will behave like a short circuit, صح?
Yes.
The inductor will behave, the capacitor will behave like an open circuit. The inductor will behave like a short circuit. So what's the final value of the current for the inductor?
Okay.
Okay. Now we're asked to find the voltage for t greater than 0, and in this case, this is the same as Yasser.
Yes, Doctor, I have a question.
Sure.
For D2, isn't it equal to IL 0 plus? Why didn't we use 29 straight for? Why isn't it D2 29 milliampere? Why is it 5 milliampere?
Because remember here, if you substitute, you take this equation. So this is the final form of the solution. So we substitute at t equals to 0. So?
Yes.
If you substitute t equals to 0, you will get IF plus D2, so?
Yeah, yes. Okay, thank you.
The voltage across the second thing that we are asked to find is the voltage. So the voltage here is the same voltage as or this is the voltage across the inductor. So the voltage across the inductor is related to the current using the following relation. So we already found the current. So we just substitute. And it makes sense here because eventually the circuit will be dissolved to, will become a short circuit here. So the voltage across the short circuit is 0, taking the limit as t approaches infinity here will result in a voltage of 0. Okay. So let's solve this last question. And we'll be done with 8.2. And this is a very interesting question because there is a very nice trick here. So we're told that there is no energy stored in the circuit. So the initial value of the voltage across the inductor, the voltage across the initial value of the current through the inductor and the voltage across the capacitor are zeros. Then the switch is closed. We need to find I of T. So what should we do here? Yes. Yeah.
Source transformation
Yes. Why?
to make it in parallel.
Yes. Because remember, the analysis that we studied so far is for parallel RLC circuit. Is this one parallel RLC circuit? No, this is not. So we can use the tool that we studied in chapter 4 to transfer this one into parallel RLC circuit by using source transformation. So if you use source transformation, you divide 25 by 125, which is 0.2. Then we'll have switch. The switch is going to close at t equals to 0. Then we have capacitor and the inductor. So when the switch is closed, we have parallel RLC circuit. 250 millihenry. This one is 6.25 microfarad. Right. Okay, now what's the next step, Shabab? When the switch is closed. Again, we're asked to find the current passing through the inductor. Ibrahim?
We should find alpha and omega naught.
Exactly.
Because the initial values are known. Just.
Yes. In this case, we need to know what type of response we have, and we cannot get any information in this regard unless we know the value of alpha and omega naught. So omega naught in this case omega naught in this case is 64 times 10 to the power 4. Alpha squared is 40 96 times 10 to the power 4. Okay. I did not show how to calculate omega naught because at this stage we are all familiar with the way of calculating omega naught. So now we can see that omega naught is greater than alpha squared or alpha. So in this case we have an underdamped response. So if we have an underdamped response, we have I naught of t is going to be I final plus B1 prime cosine omega d plus B2 prime sine omega d t And let's see what we are missing. We are missing, we know alpha, but we are missing omega d. So omega d is actually okay. Let's see. So now we need to find B1 and B2 and I final. So what is I final in this case? It's simply define the value of the current source. And this one is 0.2 ampere. This is the final value. Now, let's find the initial value. We are told that in the question statement that there is no energy stored in the circuit, which means that the initial value of the current passing through the inductor is 0. So if we take this 4 and substitute, we see that you have I final plus B1 prime, and this one is equal to 0. So B1 prime is equal to minus 0.2 amperes. Excellent. Now, we need to find the derivative of this with respect to time. So what's the derivative of this with respect to time? What's the derivative of current with respect to time? It's simply, this is equivalent to the current across the inductor divided by the inductance. But remember, inductor is actually in parallel with a capacitor. And we are told in the question statement that there's no energy stored in the circuit. So which means that the voltage across the capacitor used to be or is 0 at t equals to 0. So this one is equal to, which in this case 0. So if you take, if you differentiate I naught and evaluate it at 0, you will get 0 minus alpha B1 prime plus omega d B2 prime. So if you solve for B2 prime, you will end up with minus 0.267, and this one is also ambitious. So now we found B1, B2, B1 prime, B2 prime, and alpha, and alpha and omega d. So you can find the final value of the current, or you can find the expression for the current. So it's going to be the final value 0.2 minus B1 prime, which is minus 0.2, e to the power 640t cosine 480 t minus 0.267 e to the power minus 640t sine 480 t. The unit is ampere, and this is 1240 greater than or equals to 0. Any question? Okay, very good. Fahim?
Doctor, when we differentiate, isn't cosine omega d is constant as B1?
When you differentiate, the reason you're getting which term are you talking about?
When we differentiate I naught, we end up having B prime times negative alpha.
Yes.
Shouldn't cosine omega d be there?
Cosine omega d multiplied by t, صح?
No.
You cannot, because cosine omega d is a function of t. Cosine omega d, the argument of the cosine is omega d multiplied by t, صح? Oh, here I'm missing this.
Okay.
So, yes, you're right. The reason for that is then we evaluate it at 0. So the cosine of 0 is 1.
Okay, I get it. Thank you.
Ziad?
When we find omega d for the underdamped situation, why do we flip the omega and the alpha and not have the imaginary solution?
Because we already took care of this in the form of the solution. This form of the solution is already taking care of the fact that you have complex roots.
Okay.
So you cannot double count. You already counted.
I see. Thank you.
Omar?
دكتور، هل في إمكانية إن الهوم ورك يكون يوم الخميس السبمشن حقه؟
I don't mind if you want. You guys want.
إيه صراحة بيكون أفضل.
The only thing is like some people will complain that we have a homework that is due on the holiday.
Then I guess they can submit it at Wednesday if they want, but the others won't mind.
Okay, we can. Yeah, I don't mind pushing it. So I just point this out to Dr. Abdullah Garni.
Sorry, I didn't get it. The last part.
Yeah, I will just. I need to inform Dr. Abdullah Garni because we have coordinated homework, so I cannot make this. Cannot make a decision by my own.
تمام، يعطيك العافية دكتور.